Have you ever wondered how the food in our body converts into energy? How medicines cure illnesses? Or how fuels help in driving vehicles? Answer to all these and similar questions is a single word: chemistry. Chemistry is the branch of science that deals with the study of the composition, structure, properties of matter, and changes that matter undergoes. What is matter? Anything that has mass and occupies space is known as matter. Before we learn more about matter, it is important that we know the importance of chemistry in our daily life. It is interlinked with other branches of science and plays an important role in our daily life. How important is it in our daily life? Let's explore. Chemistry plays a major role in identifying the weather patterns, manufacturing fertilizers, alkalis, acids, salts, dyes, polymers, drugs, soaps, detergents, metals, alloys, other inorganic and organic chemicals, and new materials that contribute in a big way to the national economy. Meeting human needs in producing food, healthcare products, and other materials aimed at improving the quality of life. Producing superconducting ceramics, conducting polymers, optical fibers, and large-scale miniature of solid-state devices. Synthesizing safer alternatives to environmentally hazardous refrigerants such as CFCs, chlorofluorocarbons, responsible for ozone depletion in the stratosphere. Understanding biochemical processes and the use of enzymes for large-scale production of chemicals, and synthesizing of new materials, which have extensive uses in various fields. In order to understand the applications of chemistry in different fields and benefit from it, it is important that we know about matter. Based on the arrangement of the constituent particles, matter can exist in three physical states: solid, liquid, and gaseous. Let's look at the description of each state along with their characteristics. In solid state, the particles are held very close to each other in an orderly fashion. Hence, there is not much freedom of movement. They have definite volume and definite shape. In liquid state, the particles are loosely held together and can therefore move around. They have definite volume but no definite shape. They take the shape of the container in which they are placed. In gaseous state, the particles are far apart as compared to those present in liquid state. Therefore, their movement is easy and fast. They have neither definitive volume nor definite shape, and they occupy the available space of the container in which they are placed. The three states of matter are interconvertible by changing the conditions of pressure or temperature. For example, on heating, a solid changes to liquid. Liquid, on further heating, changes to gaseous state at normal atmospheric pressure. Similarly, in the reverse process, gas on cooling changes to liquid, and on further cooling, liquid changes to solid. Matter can be classified as pure substances and mixtures based on the chemical composition. Substances which contain only one kind of atoms or molecules are called pure substances. And in a pure substance, the composition of a substance is fixed. For example, carbon dioxide is a pure substance which consists of only molecules of carbon dioxide, and it has carbon and oxygen in a fixed ratio. When elements or compounds are mixed together in any proportion, it results in the formation of a mixture. Thus, in a mixture, the composition varies. For example, seawater comprises of dissolved salts and water. The seawater consists of varied amounts of dissolved salts and water. Pure substances can be further classified into elements and compounds based on separation of it into its respective constituents. Substances which consist of only one kind of atoms are called elements. Examples of elements are sodium, copper, silver, hydrogen, oxygen, etc. An element cannot be further separated into its constituents by physical or chemical means. For example, oxygen consists of only oxygen atoms, and it cannot be further separated into its constituents, that is, oxygen atoms. Two or more elements combine chemically in a fixed proportion to form a compound. Examples of compounds are ammonia, water, etc. A compound cannot be further separated into its constituents by physical means, but can be separated by chemical methods. For example, oxygen and hydrogen are present in a 1:2 ratio by volume in water, and water, that is H2O, can be separated into its constituents, hydrogen and oxygen, by electrolysis, but cannot be separated into its constituents by any of the physical methods such as distillation, fractional distillation, etc. Also remember that the properties of a compound are different from those of its constituent elements. For example, the elements hydrogen and oxygen, being gaseous in nature, combine to form a compound, water, which is a liquid. Mixture can be classified further based on the uniformity of the particles present in it. If the particles are distributed uniformly throughout the solution, then it is a homogeneous mixture. For example, sugar solution is a homogeneous mixture because sugar particles get distributed uniformly throughout the solution. If the particles are not distributed uniformly throughout the solution, then it is a heterogeneous mixture. For example, sand dissolved in water is a heterogeneous mixture because sand particles are not uniformly distributed throughout the solution. A mixture can be separated into its constituents by physical methods. For example, a mixture consisting of iron filings and sulfur powder can be separated by using a magnet, that is, by magnetic separation. As we learnt, matter is anything that has mass and occupies space. Every substance is made of matter and has unique properties. We can classify properties as physical and chemical properties. Let's learn about them. We have with us a rubber ball. Let's see how we can describe it. By looking at and feeling the ball, we can see that the ball is a solid. It is round and yellow in color. It smells like rubber and it bounces. Now, let's observe this block of sulfur. We can say that sulfur is a yellow solid crystal and has a strong odor. What we saw are the physical properties of a rubber ball and sulfur. These properties can be easily seen or felt. Thus, we can say that physical properties are those properties that can be measured or observed without changing the identity or the composition of the substance. Color, length, mass, area, texture, elasticity, odor, melting point, and boiling point are examples of physical properties. Physical properties help us describe a substance. However, the description is not sufficient to identify a substance. For example, saying that sulfur is something that is yellow and solid and has a strong odor is not enough, because there can be many solids that may have the same properties, including our yellow rubber ball. Hence, it is necessary to also know the chemical properties of a substance to identify it correctly. The chemical properties of a substance can be observed when a substance undergoes a chemical change. Flammability, reactivity to an acid, and reactivity to water are examples of chemical properties. For example, if we burn sulfur, it produces a blue clear flame. Thus, the blue clear flame is a result of chemical property. When performing a chemical experiment, scientists study the properties of substances. This involves measuring the quantitative properties of a substance. A quantitative measurement comprises a numerical value and a unit. For example, this block of sulfur weighs 200 grams. Here, 200 is the number and grams is the unit. The units of measurement are derived from two systems, the English system and the metric system. The English system included units such as yard, foot, inches, miles, and gallons, to name a few. However, there was no uniformity in the conversion of one unit to another. In 1791, the French Academy of Science introduced the metric system. Under the metric system, the units of physical quantities relate to each other as multiples of power of 10. For example, 1 kilometer equals 10 to the power of 3 meters. This system was found to be convenient and hence was used worldwide. In 1960, the metric system was improved at the General Conference of Weights and Measures to create a new system called the International System of Units, or SI, which is short for System International in French. The SI unit pertains to 7 fundamental scientific quantities. They are length, measured as meter, mass measured as kilogram, time measured as second, electric current measured as ampere, thermodynamic temperature measured as Kelvin, amount of substance measured as mole, and luminous intensity measured as candela. Let's look at each quantity one by one. The SI base unit of length is meter. Meter is the length of the path travelled by light. In vacuum, during a time interval of 1/2997/92458 of a second. The SI base unit of mass is kilogram, which is equal to 2.2 pounds. As per the SI unit, kilogram is the mass of a specific cylinder of platinum-iridium alloy kept at the International Bureau of Weights and Measures in France. Thus, it can be defined as the mass of the international prototype of the kilogram. The SI base unit of time is second. It is based on the radiation from the cesium-133 atom and is defined as the duration of 9192631770 periods of the radiation, corresponding to the transition between two hyperfine levels of the ground state of the cesium-133 atom. The SI base unit of electric current is ampere. It is named after André-Marie Ampère, a physicist who discovered electromagnetism. It is defined as the constant current which will produce an attractive force of 2 × 10⁻⁻⁷ Newton per meter of length between two straight, parallel conductors of infinite length and negligible circular cross-section placed 1 meter apart in a vacuum. The SI base unit of thermodynamic temperature is Kelvin. It is the fraction of 1/273.16 of the thermodynamic temperature of triple point of water. The SI base unit to measure the amount of substance is mole. Mole is the amount of substance which contains as many elementary entities as there are in 12 grams of carbon. Elementary entities may be atoms, molecules, ions, or electrons. The seventh unit on the SI base unit is candela. Candela is the luminous intensity in a given direction of a source that emits monochromatic radiation of frequency 540 multiplied by 10⁻⁻12 Hz and has a radiant intensity in that direction of 1/683 watt per steradian. Now, let's look in detail at some common quantitative measurements that we will come across in our modules. These are mass, volume, density, and temperature. Think about it. Is mass the same as weight? Oftentimes, people consider mass and weight to be the same things. However, that is not the case. Mass is the amount of matter present in a substance, while weight is the gravitational force exerted on a substance. This implies that the mass of a substance remains constant, whereas its weight may differ from one place to another due to change in the gravitational force. For example, a person's mass is 120 kg on Earth and the calculated weight is 1,200 Newton. If you weigh the same person on the Moon, his mass would be the same, while the weight would differ. In this case, 200 Newton. This is because the gravitational force of Earth and Moon differ. Mass can be accurately measured with the help of analytical balance. Now let's look at volume. The base SI unit of volume is cubic meter. Smaller units, such as cubic centimeters, are frequently used in chemistry. Another unit of volume that is commonly used is liter. 1 liter equals 1 cubic decimeter or 1000 cubic centimeter. Some of the common devices used to measure volume of liquids are the graduated cylinder, burette and pipette. Density is the amount of mass per unit volume of the substance and can be illustrated as shown in the equation. As this unit is large, chemists often express density in grams per cubic centimeter. Finally, let's look at temperature. There are 3 scales used to measure temperature: degree Celsius, degree Fahrenheit, and Kelvin. The Celsius scale is the most common unit for temperature, and we learned that the SI unit for temperature is Kelvin. So, let's see how the 2 scales are related. The Celsius and Kelvin scales are divided into 100 equal parts. 0 degree Celsius is equal to 273 Kelvin. Thus, we can say that the temperature in Kelvin equals temperature in Celsius plus 273. Note that, unlike Celsius and Fahrenheit, temperature in Kelvin is not referred to as a degree. Now, let's see how the Fahrenheit scale relates to the Celsius scale. The Celsius scale is divided into 100 parts, while the Fahrenheit scale is divided into 180 parts. The freezing point of water on the Celsius scale is 0 degrees, while on the Fahrenheit scale it is 32 degrees. So, 100 Celsius degree equals 180 Fahrenheit degrees, or 5 Celsius degrees equals 9 Fahrenheit degrees. We have learnt that chemistry deals with matter, and matter is made up of atoms and molecules which have extremely low masses and are present in very large numbers. Thus, chemists have to deal not only with a large number of atoms and molecules, but also with calculations containing large numbers. For example, Avogadro number is such a big number that there are 20 zeros after 6022. It is not only inconvenient to write such a large number, but also difficult to perform mathematical operations like addition, subtraction, multiplication, or division with such a number. To overcome this problem, chemists started writing large numbers using scientific notation, also known as exponential notation. In scientific notation, any number can be represented as n multiplied by 10 to the power of n, where lowercase n is an exponent having positive or negative values, and uppercase n is a coefficient that can vary between 1 and 10. Thus, we can write Avogadro number in the exponential form as 6.022 multiplied by 10 raised to the power of 23. Similarly, the number 0.049364 is written as 4.93604 multiplied by 10 raised to the power of -2. Here, we have to move the decimal point 2 places to the right. Hence, we can say that the exponent is -2 and the coefficient is 4.93604. Now let's see how to perform mathematical calculations on numbers written in scientific notation. Let's start with addition and subtraction. If we have to add or subtract any number expressed in scientific notations, we must first check if the exponent of the numbers is the same. Only if they are same, we can add or subtract the coefficients. For example, in this equation, one exponent is 4 and the other is 3. Therefore, in order to add the numbers, first we have to make the exponents same. As 6.62 has the larger exponent, that is 4, we have to convert the exponent of 4.31 to match the larger exponent. So, we rewrite 4.31 multiplied by 10 raised to 3 as 0.431 multiplied by 10 raised to 4. Now, after taking the exponential factor in common, we add both the coefficients and obtain the result as 7.051 multiplied by 10 raised to the power of 4. The same rule applies to subtraction. The example shown here illustrates the steps to subtract two numbers. Now let's see how to multiply and divide numbers written in scientific notations. To multiply two numbers, first we add the exponents and then multiply the coefficients. For example, to multiply 2.4 multiplied by 10 raised to the power of 3 with 5.6 multiplied by 10 raised to 4. First, add the exponents and then multiply the coefficients as shown. To divide two numbers, first subtract the exponents and then divide the coefficients. Here's an illustration of dividing numbers written in scientific notations. When performing experiments, we often perform mathematical calculations on quantitative measurements to obtain accurate results. People often use the terms accuracy and precision interchangeably. But, are accuracy and precision the same? Let's see. If we have few grains of rice scattered in the plate, we can easily count them and say that they are 20 in number. However, what if we were asked to count the rice grains in this bowl? We would count them, but due to the large quantity, we may not be able to confirm if our count is accurate. One way of ascertaining the accuracy of measurement is to repeat it. Let's assume that we know that there are 105 grains in the bowl. Thus, the correct value of measurement is 105. Now, let's say we ask 4 people to count the grains, each 5 times. Shown here is the data of each person. We know that the correct value is 105. If the average value of one of the measurements is close to the correct value, then that measurement is said to be accurate. If the values of measurements are close to each other, and hence close to their average value, then the measurement is said to be precise. Let's look at the data to understand what it shows us. For person A, the average value matches the correct value. Also, the values of different measurements are close to each other. Hence, we can say that A's data is accurate and precise. For person B, the average value is not close to the correct value, but the values of different measurements are close to each other. Hence, B's data is not accurate, but it is precise. For person C, the average value matches the correct value, but there is a variation between the values of different measurements. So, C's data is accurate but not precise. Note that accuracy without precision could be a matter of chance. For person D, the average value does not match the correct value. Neither are the values of different measurements close to each other. So, D's data is neither accurate nor precise. The certainty and uncertainty in a measurement is indicated through the use of significant figures. Significant figure is the total number of certain digits in a number, including the last digit whose value is uncertain. The uncertainty is indicated by writing the certain digits and the last uncertain digit. For example, if a measurement is reported as 16.3 ml, we can say that the 16 is certain and 3 is uncertain, and the uncertainty would be plus or minus 1 in the last digit. Let's see the rules to determine the number of significant figures in a reported quantity. The first rule says that all non-zero digits are significant. For example, 897 has 3 significant figures. 0.23 has 2 significant figures, and 9.87 has 3 significant figures. According to the second rule, zeros preceding the first non-zero number are not significant. Such zeros indicates the position of decimal point. For example, 0.0325 contains 3 significant figures. The third rule is zeros between 2 non-zero digits are significant. For example, 5.01 contains 3 significant figures. The fourth rule is all zeros placed at the end or to the right of a number are significant, provided they are on the right side of the decimal point. Therefore, 0.400 has 3 significant figures. However, terminal zeros are not significant if there is no decimal point. For example, 100 has only 1 significant figure. The fifth rule says that the exact numbers or numbers that are obtained by counting rather than measuring are assumed to have infinite significant figures. For example, 8 apples have infinite significant figures, as 8 is an exact number and can be represented by writing infinite number of zeros after placing a decimal, that is 8.000000 infinitum. Now let's see how to determine significant figures in the results of mathematical calculations. While adding and subtracting numbers, the result should have the same number of digits to the right of the decimal places as the original numbers have. For example, if we add 16.25, 22.0 and 2.062, we get 40.312. Here, as 22.0 has only 1 digit after the decimal point, the result should be reported only up to 1 digit after the decimal point, which is 40.3. While multiplying, the result must be reported with same number of significant figures as there are in the measurement with few significant figures. For example, if we multiply 12.984 by 2.5, the result is 32.46, which should be rounded off to 32, as the number 2.5 has only 2 significant figures. Similarly, if we divide 5.7634 by 1.28, the result is 4.5027. According to the rule, the result must be reported with 3 significant figures. Thus, the correct answer is 4.50. Now let's look at the rules for rounding off significant figures. The first rule is, if the last digit is greater than 5, then the preceding number is increased by 1. For example, in 1.347, if 7 has to be dropped, then the number is rounded off to 1.35. The second rule is, if the last digit to be removed is less than 5, then the preceding is not changed. For example, in 5.332, if 2 is to be dropped, then the result is rounded off to 5.33. The third rule is, if the last digit to be removed is equal to 5, then the preceding number is left as is, if it is even, else it is increased by 1. For example, if 7.45 is to be rounded off by removing 5, then it is rounded off to 7.4. However, if 7.35 is to be rounded off, then we have to increase 3 to 4, giving 7.4 as the result. When we perform mathematical calculations, sometimes we need to convert units from one system to another. This can be achieved through a method called factor label or unit factor method, or dimensional analysis. Let's understand this through an example. Assume that we have to convert the length of the object from inches to centimeter. We know that 1 inch is equal to 2.54 centimeters. We can write the equation as 1 equals 1 inch divided by 2.54 centimeters, or 1 equals 2.54 centimeters divided by 1 inch. The quantities 1 inch divided by 2.54 centimeters and 2.54 centimeters divided by 1 inch are known as unit conversion factors because they convert a quantity expressed in one unit to a quantity expressed in another unit. For example, if we want to convert 5 inches to centimeters, then multiply the given quantity by suitable conversion factor, retaining the units of the physical quantity and that of the conversion factor. Cancel out all the units, leaving behind only the required units. This means that numerator should have that part which is required in the desired result. Thus, 5 inches is equal to 5 inches multiplied by 2.54 centimeters by 1 inch. Thus, 5 inches is equal to 12.70 centimeters. Also note that if the conversion involves many steps, then the conversion factors are selected in such a way that the units of the preceding factor are cancelled out. Let's see an example. Let's say that we have to find the number of seconds in 3 days. We know that 1 day is equal to 24 hours. So we write the conversion factor as shown. We also know that 1 hour is equal to 60 minutes and 1 minute is equal to 60 seconds. In this calculation, we want the answer in seconds. Hence, we will select the conversion factors in such a way that the units of the preceding factor are cancelled out. Thus, in this equation, hours, minutes, and days are cancelled out, and we obtain the answer in seconds.